I'm Tim Ventura, and we're joined today by Gene Greneker, CEO and Chief Scientist of Radar Flashlight LLC, a small business conducting radar research for industry and government. Prior to his current role, Gene served as Principal Research Scientist at Georgia Tech Research Institute before retirement, where he directed over 60 major sponsored research projects for many of the U.S. government agencies and military services, mostly related to radar technology. In addition to his technical expertise in radar, Gene's career includes experience as director of the Georgia Tech Research Institute's Severe Storm Center, conducting tornado research for the state of Georgia. Gene's expertise in radar detection includes diverse applications, including weather pattern analysis, the detection of airborne smugglers and waterborne threats to U.S. nuclear submarine forces, advanced transportation systems detection, physical security of DOE nuclear facilities, marine radar navigation, radar entomology, radar meteorology, and more. He joins us today to discuss yet another use of radar, the detection and tracking of unidentified aerial phenomena. Gene, welcome, sir. It is truly a pleasure and an honor to have you with me here today.
Tim, thank you very much for having me today. I'm looking forward to our brief discussion here.
Well, I am really excited. I saw your presentation at the 2025 SCU conference, and so I definitely want to put a plug in there for the SCU. People should visit and sign up and get involved at explorescu.org. And I wanted to see how was the presentation received? What kind of feedback did you get from it?
Tim, the presentation, I think, was well received. Got several questions after the presentation, and I was contacted by a number of the SCU members with additional questions that did not get asked online. So I think all in all, the topic was well received, and I think there's interest in this topic.
Well, your experience is just, there is no comparison, right? You have an entire career in radar, and you've taken on several of these, what we might call experimental projects. Passive radar that's been a long time interest of mine now. And, I think one of the things that attracts people in the SU to it is when it comes to UAP, we have so much photographic and video evidence, but a lot of that is blurry. It's hard to tell what's going on. Sometimes it's difficult to tell what may or may not have been faked. And so radar has been the gold standard for detecting UAP, right? And if we're able to combine that with the visual analysis that's there, that could open up a whole new world to detection, tracking, and analysis.
Well, you're absolutely right, Tim. When you use radar, you are getting a return or a reflection from an object. You know what the transmitted signal is, and when the signal comes back to you, there are ways of checking that signal to make sure that it was the transmitted signal. So that removes a lot of the fakery. And it also tells you that there is something in the airspace there that does reflect and obey the laws of physics. So at least that's what we think at this point in time.
Well, so let me do a little bit of historical analysis here. The Washington UFO flap of 1952, I think that was probably one of the biggest, earliest radar incursions of UAP or UFOs, right? And that was a series of sightings that happened between July 12th and 29th, 1952. It led UFO historian Curtis Peebles to say, never before or after did Project Blue Book and the Air Force undergo such a tidal wave of UFO reports. Now, the U.S. Air Force later speculated that it was actually a temperature inversion causing those radar contacts. So I wanted to ask your thoughts. Do you think that could have been a temperature inversion, or was there actually some kind of a craft that they were detecting?
Well, I actually did some research on that, Tim. And what you find is that just after the Washington flap occurred, Air Force Geophysics Lab and some of the other labs that work for the Air Force did an extensive study. And in fact, the big instrumentation radars on Wallops Island were also used in the study. And they came up with a term called radar angels. Radar angels are basically an atmospheric effect that occurs, and it does reflect these very tight areas of I just want to say strange atmosphere do reflect radar signals, and they travel with the wind, and there are other possible explanations and other characteristics too. And so after the Air Force did their studies after the flap, then it came back, official word, that no, what was being seen in Washington was strictly these angels, inversions, if you will, although an inversion is different than an angel. Inversion usually occurs over a wide area. The angel is a very tight, compact type target that is really an anomalous area in the atmosphere, small anomalous area in the atmosphere. And so that's how we got the word that the Washington flap, as far as the radar went, uh, were probably these objects were radar angels.
Okay. Well, and again, you have this incredible career with radar. Have you seen radar angels? And for that matter, have you seen UAP on radar? Over the course of your career.
Well, I did a study using the terminal Doppler weather radar operated by the FAA to detect downdrafts and other downburst phenomena along the runway that can bring an aircraft down. And these radars are very, very sensitive. And I have seen what looks like discrete targets traveling with the wind, but they're interesting from a phenomenology standpoint in that they travel with the wind at the speed of the wind. They stay in the beam of this pencil beam radar that has a 0.5 degree beam width for maybe an hour, up to 2 hours. They are small, tight targets. As far as qualifying, they are true UFOs, but can they be explained as a weather event or a radar angel? That's the question.
Yeah, well, and it's intriguing because, again, you have worked, I mean, having worked at the Severe Storm Center, right? You've worked with extreme weather conditions. You've looked at tornadoes up close on radar and things like that. So, it's intriguing to see that you've seen things like this on radar. Now, if I could jump back to 1952, I've got some notes I want to get through here. Philip Klass, senior editor for Aviation Week magazine, was quoted as telling a reporter radar technology in 1952 wasn't sophisticated enough to filter out ordinary objects such as flocks of birds, weather balloons, or temperature inversions, or angels, as you mentioned. He also added that the introduction of digital filters in the 70s led to a steep decline in UFO sightings on radar. And the reason that I wanted to read his quote was there are a couple of points there. The first one is radar can produce false positives, right? That's something that we need to be aware of. But secondly, it seems that UAP may have been automatically filtered out of many radar systems for over 40 years now, right?
Okay, well, let's talk about what I believe Philip Klass was actually saying. Um, when he was addressing the fact that the air traffic control radars did not filter out objects, to me, that says, well, it should have been able to detect a UAP because now in the modern air traffic control radars, there is what used to be called a moving target indicator. That is to say, any detected object moving below, and I'm just going to pick a number, 30 knots, will not be displayed on the screen.
Okay.
That gets rid of the birds. That gets rid of the land clutter, the other type of clutter. In fact, they use polarization to try to get rid of the weather clutter. So the antenna is circularly polarized, and there are other filters that are applied to targets in modern air traffic control radar. Back in the 1950s, these radars simply swept, and anything that they saw or they got reflections from was put on the display. Well, for detecting UAPs, that's exactly what you want, because when you look at the flight characteristics of a UAP, it can hover. From that hover, it can depart at speeds in excess of supersonic velocities. And you don't want any filtering if you're going to try to go for UAPs. So, in a way, that was the perfect setup, those old radars that if we get a reflection, we're going to put it on the screen. But that reflection and the motion of that target, once placed on the screen, has to be analyzed and has to be recognized to determine whether it's a UAP type object or whether it's birds or weather or the other clutter that he was talking about, I think.
Well, so yeah, I'm jumping around my questions a little bit here, but with normal radar, you have a sweep, right? You have a beam that goes out. And so in terms of UAP, you mentioned it hovering and taking off at high speed. That's something where the sweep could potentially miss that, right? It would be there and then it would be gone the next moment.
Well, in the early radars, the radars swept. Every 12 seconds they would sweep approximately 360 degrees, come back around and refresh that target on the display. And the displays had phosphor, long-term phosphor, so that area would stay lit for at least one sweep. And so the radar operator would associate in his or her mind, okay, this is a target. Okay, now the next sweep shows it's moved half an inch on the screen, and the calibration would tell you, okay, that corresponds to 3 miles or 5 miles or something like that. Well, in the case of a UAP, let's say it's hovering. If you don't have a filter that filters out the ground clutter, you're probably not going to see that, because there's going to be all kind of these random targets just on the screen. But let's suppose that you had a UAP on a clear screen. With the current radars that we have today, with the trackers, these modern trackers that say, okay, I see a return here, 12 seconds later I see a return there, and maybe it's 5 miles away, then it says, okay, if I see it again, I'm going to declare a track on that target. So yes, it sees it again, and again it's 5 miles from where it was before. And I'm just pulling numbers out of my 10-gallon hat here, but basically what happens is this tracker then forms a track, and it declares a track, and it puts that on the screen, and that's what the radar operator is looking at. Well, in the case of a UAP sitting absolutely still, it has to start moving before the radar tracker will even consider it a target worth considering as an object in the airspace. So all of a sudden it takes off at this supersonic rate. First track point is 15 miles away from where it was the previous sweep. Then the next track point is another 30 miles away from where it was, and the tracker says, I only know how to track aircraft velocity type targets. I don't know how to track a UAP type target. And it never declares a track. So that's another failure of the modern air traffic control radar, to be able to detect and track a UAP if the UAP is not moving at aircraft velocity, like an airliner or a private aircraft.
Okay, that's a really important point. So, commercial radar systems, the kind that are used by air traffic control, simply aren't calibrated to deal with unidentified aerial phenomena. And military systems may not be calibrated the same either. Right? They have different calibration settings because they may be looking for, inbound missiles or things like that. But, you know, UAP could be evading, I guess, or simply filtered out of both of these types of systems.
That's right. The UAP could be filtered out. For example, you remember the Chinese balloon.
Yeah.
That balloon was moving at such a slow velocity that it did not clear the moving target indicator velocity for display. So as a result, uh, the radars were not displaying the balloon payload, and they were detecting it just fine, but it was too slow for the tracker to say, okay, I'm going to consider this a target.
Well, I appreciate you mentioning that. I actually have a quote about that from Reuters. They wrote, officials say a key change was to NORAD's filters to allow them to detect objects moving slowly and at different altitudes without specifying which one. So again, back to filtering and, kind of the automated algorithms that go into radar, right? And if I understand this correctly, there are a lot of things like you mentioned angels, at the top of the show. You mentioned lots of like atmospheric effects that may play a role, flocks of birds, things like that. And so when you get into things like definitely air traffic control, but also military systems, you're looking for specific targets, right, that may represent an aircraft or could potentially represent a threat in the military case. You don't want to see everything because you're going to have a lot of noise.
Well, there's a saying in radar, one man's target is another man's clutter. And that's why they go to the extent they do. If your job is to detect, let's say, border smugglers coming across the border, you want your velocity filter set up for a private aircraft, for example. If your job is to control aircraft of all velocities, you want your filters set up for that, and you want it to be maximized for that. There's also another thing going on here. Air traffic controllers will never see a UAP unless the pilot, let's say we have a pilot like the Japanese airliner in Alaska, who sees a large UAP and he calls air traffic control and says, do I have a target near me? They had to switch over from the transponder channel, which is what they're using to track aircraft, over to the what's called the primary radar channel, which is the channel that is displaying the reflected energy from the aircraft, in order to see that UAP that was following the Japanese freighter that was seeing the UAP outside the cockpit.
So, in other words, they were following the transponder signals of aircraft on the screen. They wouldn't have seen anything that didn't have a transponder.
Well, basically what happens, Tim, is that if you're an air traffic controller, you want to see all the symbology. Let me back up. On an air traffic control radar, you have the primary radar, which is the antenna and transmitter receiver that is transmitting a signal. It's bouncing off or reflecting off of the aircraft and coming back, and based on where the antenna is pointing, that's the azimuthal bearing to the aircraft, and based on the time that it takes for the signal to go out and return, that is the range to the aircraft, and that's how that XY position gets put on the scope. In the case of the secondary radar, which is associated with the primary radar, they're at the same place, but they have different antennas, different receivers. The secondary radar sends a signal to the aircraft, and on board the aircraft is what's called a transponder. The transponder says, oh, they're talking to me. They want to know where I am, what my altitude is, so I will encode that digitally and I will send it back to the air traffic controller's display. Well, when that comes back, the air traffic controller now has a neat little target, no clutter, no anything, just a neat little target that says, this target is Air Force 351. He's at 25,000 feet. This is his position, and this is his airspeed. All that information comes from the transponder return. Why would an air traffic controller look at returns from the primary radar on a cluttered scope, and he doesn't know who anybody is, he just knows their returns from the aircraft, when he has that transponder information? And in fact, even there's a better system out now called ADS-B, and that's a broadcast, and you get the GPS coordinates, you get a whole lot more information, and in the near future, probably the FAA will go to using ADS-B data instead of the primary transponder, the primary radar and the secondary radar that's looking at the transponder. So all of this is evolving, but if you want to go back to the old cases, no air traffic controller wants to sit there and look at a cluttered display like they used to in World War II.
Yeah. Well, and I appreciate your outlining kind of the technology today and a little bit about how it has evolved. And for me, it simply highlights the fact that UAP could easily be missed by radar. They simply wouldn't show up. Now, I want to get into passive radar. This is something that you are actually experimenting with. You have built a passive radar system yourself. This is an area that I've been really excited about because it seems like, in a sense, it democratizes radar detection of UAP. So I want to ask a little bit about how that works. If you could kind of walk me through that.
Sure. Well, basically, the FAA, Federal Aviation Administration, the U.S. Air Force, are not going to give the citizen scientists their data from their radars. There are a number of reasons for that, some valid, some not so valid. But anyway, that's the case. Well, if the citizen scientist wants to use radar to detect UAPs, there's a class of radar called a passive radar. The passive radar takes signals that are already out there being used for something else. For example, an FM broadcast or a high-definition television signal. Takes that signal, detects when it bounces off of an object, an airplane, something in the airspace, and then displays that information on the citizen scientist receiver located in his own home. And of course, basically, there are two types of these passive radars. One is called the Doppler rate radar, and it looks for the Doppler shift generated when the aircraft is moving in the airspace. So a signal goes out, let's say from a high definition television station, reflects off of a moving aircraft and comes back at a Doppler shifted frequency. And so if you have a receiver at home that can receive that Doppler shifted frequency, and you have special software that has been written to display how far that Doppler shift is from the non-moving direct path signal that's also displayed on the display, then you know if you have a moving object in the airspace. Now that's called the Doppler rate, and that's very simple, very easy to achieve, requires probably one Yagi antenna and one receiver that's capable of receiving whatever your signal source is. There's another passive radar that uses both range and I want to say here by static range, not real range, but it can give you an idea if a track is linear and moving as it should for, say, an aircraft versus maybe a track that is moving in different directions or 90 degrees. You know, track moves along, and then all of a sudden it starts going 90 degrees to the bearing or to the heading that the object is flying, or perhaps the Doppler goes from a reasonable rate for an aircraft to some supersonic Doppler. That second type radar can detect all of that, but then you have to make some decisions as to whether, do I really believe this data? Well, if you want to go a little more sophisticated, they're now taking, say, 4 of these range type radars that produce both range and Doppler. If you take 4 of those, you then send the information from each of those 4 via the internet to a central server. That central server can figure out exactly not what the bistatic range is, but the actual location of the target. And of course, that's much better. So the citizen scientist soon, I think very soon, is going to have a system that can be purchased and operated from home and set up at home with 2 small TV antennas in the backyard.
Now, again, this is something that you have constructed. You are operating one of these yourselves. I've talked to you on the phone a couple of times over the last week, and you've described these. What excites me about this is for a few $100s, right? I think the price range is like $500 to $700. You could quite literally have a radar system that you can operate yourself to detect UAP. And that is just mind-blowing, right? So if for people who live in a hotspot, because I know that there are various hotspots across the United States, if they set one of these up, I think that they might have something like a 60-mile range, right, where they could see them?
Typically, yes. I have one set up at my home. I'm using a high-definition television transmitter that's about 30 miles south of my home. It's putting out around 60,000 watts of power, and based on my location and its location, I can detect targets maybe 30 to 40 miles away very reliably. And what these targets leave are a track, a trail, if you will, across the passive radar display. No, it's not exactly where the target's located, but you can certainly look at that track and see if it is deviating from its current bearing 90 degrees off. And you can get a very good idea if you're seeing something that might be an anomalous type target.
Okay, so it depends on the power of the electromagnetic background noise, what the range actually ends up being.
Well, certainly there is the system noise that you have to consider, and the gain of your antenna, that is how much multiplied signal the antenna gets because it's directional. And that's what I have been using for the past 6 months. Now, I'll very quickly tell you, I have not seen any type of UAP target. I operate that system late at night because I'm in the Atlanta area, and the Hartsfield International Airport in Atlanta pumps out 100 flights going over my house every hour, and it's very hard to separate airliner traffic from possible transiting UAP type target. And so I operate early in the morning. I keep my eye on the display. I might be writing software, doing something else, and I have not seen a UAP type target, or what I would consider a UAP type target. But there might be a reason for this. I really am coming to believe that the probability of seeing or detecting a UAP at any point in the continental United States, the probability is very low.
Yeah.
Yes, if you look at the databases, maybe 10 are detected every week. But if you say, okay, my receiver is in Atlanta, what's the probability of a UAP transiting through my area? When I'm looking at the radar, the probability is fairly low, I think, based on my experience.
Oh, I completely agree with that. I think because we focus on UAP, right? We have this interest area and we have this focus on it. It's like what do they say? What you focus on expands. And so, people tend to think UAP are everywhere all the time, but in reality, these events are very rare, right? These are exceptions. They're not
Yes,
the rule. So, you
yes.
know, yeah. So I think a lot of it would be doing what you're saying. You have the screen up and you look at it periodically, you know. Um, so in addition to passive radar, you told me about something called Homodyne radar, which is kind of like a police speed gun.
Yes.
And the interesting thing about that was you'd said that this could pick up basically audio signals, if I understand that correctly.
Okay. Basically, a Homodyne radar is one, as you point out, like a police radar. Homodyne means it's self-referencing. When you take these inexpensive microwave generation modules at 10 gigahertz, uh, you find they're very unstable. But if you're using their own signal to beat against the incoming signal, which is transmitted by their own little unstable transmitter, what falls out is a very stable Doppler reference. Now, if you are looking, say, at 10, if you're using a frequency of 10 gigahertz, the Doppler shift is roughly 31 hertz per mile per hour of the target. So if the target is coming directly at you at 100 miles an hour, that would be what, 3,150 hertz. So you would hear a tone of 3,150. There are plasmoids being reported as UAPs, and in fact being investigated as UAPs. And these plasmoids are reported to be these large glowing orbs.
Yeah.
Now, if we assume that that orb is actually plasma, plasma will reflect microwave energy. So if they're sitting absolutely still, hovering, and this orb has this very disturbed plasma that's moving around inside of the orb, you might, using a Homodyne radar, determine something about the physics of this orb. You wouldn't hear 3,150 hertz, but you might hear 30 hertz or 40 hertz, and that would tell you, okay, this is the actual plasma as it expands, contracts, or whatever it's doing, and that might give you a clue. So yes, hopefully we're going to be able to get maybe one of these Homodyne radars built and out into the field for these researchers, UAP researchers, who are very serious, and they're actually going to the field, and there is a long history of a hotspot where they're going.
Yeah. Well, I appreciate you providing that drill down on it. It's exciting to me, this idea of being able to collect as much data as possible across as many spectrum as possible, right? And with radar, since you're measuring microwave frequencies, I'm wondering if you can also measure like electromagnetic emissions as well. Is that something that you can pick up with these systems?
There is on the internet, YouTube, for example, there's a group of radio astronomers who, buy themselves a 2-3 foot parabolic dish. They use a very low noise preamplifier, and typically they're working at a frequency of 1.4 gigahertz, which is called, or 1.420 gigahertz, which is called the hydrogen line. And they're looking at atomic hydrogen, the radiation from atomic hydrogen in the galactic areas around the galactic center, that sort of thing. This particular type approach would work very well for determining if a UAP has a self-emission of microwave energy, and a broader spectrum analyzer, a spectrum analyzer with a little broader coverage, could very easily tell you that you have an emission from a UAP. Nobody knows what frequency it might be on. There have been I believe two instances of emissions being detected by military systems. And basically, it'd be nice if through freedom of information or something else, somebody could say, okay, well, if you're going to look for these emissions, look around 2.1 to 2.9 gigahertz or whatever the investigation determines. Because what you find out when you look at just a broad spectrum of frequencies, which is what you have to do if you have no a priori knowledge of what you're looking for, there are a lot of signals out there.
Yeah.
Many of them are very transient. They move. They don't occur all the time. They pop up, they pop down. And how you get a handle on, okay, this is from a UAP, and this is from a HD TV transmitter over the hill, or this is from a satellite, or this is from some transitory source, very hard to detect and, really confirm. Is confirmation at that point.
Oh, I see what you mean. And, that reminds me of things I've heard from the astronomy community as well, right? Like they'll pick up an anomalous signal and they say, could this be from another star system? And it turns out it's actually from a satellite. I've heard stories about things like that. So, yeah, the same would absolutely apply, probably even more so to things that are terrestrial, right? Because you have so many different machines and equipment and reflections and things emitting electromagnetic energy and not necessarily identifying what it is.
And two, the other thing, Tim, every time the Russians put a satellite up, or the Chinese put a satellite up, or somebody else with satellite launch capability, they don't go to the world and say, okay, these are the signals we're transmitting, these are the times they're on, these are the frequencies. They're just there. And if your antenna is pointing vertical or somewhere along the horizon, you probably are going to see some signals that you don't know what's there.
Yeah.
In addition, the United States even has satellites that they do not want anybody to know where they are or what they're doing. But these satellites are also transmitting information. So it's very tough sorting the trash from that one UAP that might move over very slowly and be emitting a signal.
Well, that's an excellent point. So far, we've talked about passive radar, and you can have multiple antennas for that, right? It'll work with one antenna, but the more antennas you have, the better you can pinpoint where a source is.
Well, for passive, Tim, you want, if you're doing the simplest system, which is Doppler rate, you only need one antenna, and you null the direct path signal from the signal source out as much as you can, and then you just look at Doppler shift. For the range and Doppler passive radar, you need two antennas. One looks directly at the signal source and gets a perfect signal. The other looks in the target area, which is away from the illuminating signal source, and you try to null out the illuminating direct path signal from the target channel, because it can overload the front end of the receiver and keep you from seeing those very weak echoes that are coming off the aircraft of the UAP.
And then, in addition to that, you talked a little bit about the Homodyne system. And again, that's a little bit more like a police speed gun. I wanted to ask, are there other systems that might be available to the citizen scientist?
Well, basically, you might get by with something as simple as a marine radar on suction cups on top of your truck or truck cab or your car. And if you are in a hot spot, and if you have been sighting this object on a regular basis, something as simple as a small boat marine radar works very well for that. It'll give you the range to the target. It'll give you the azimuth of the target. You know, a light in the sky is very deceptive as far as range and azimuth. Well, azimuth you can point to, but range you don't know whether it's close, you don't know whether it's far away. So certainly just using something as simple as the marine radar would allow you to calibrate your optical instruments as far as range go.
Okay. Well, and the reason I ask about that is, at least traditionally, right? Most UAP sightings start with the eyes, and nowadays, it goes from the eyes to a smartphone of some kind. And so, if you've got the optical data, if you're able to have something, again, you just mentioned a marine radar to help back that up, then you've got the beginnings of multimodal detection, right? And
That's right.
if nothing else, it helps to validate, is that a really bright star, or is it like, glare off a satellite antenna, right? Like an iridium flash, if I remember right. Or is this some kind of a craft plasmoid object moving in the atmosphere? So,
Well, certainly if you see a light in the sky, you had a marine radar with the display in the cab of your truck or your car, and you're detecting that object, say at, I don't know, 10 miles, something like that, it's real. You are confirming with two sources, detection sources, that it's there, and the radar is giving you the actual range and the azimuth, and that aligns with what you're seeing visually. I say that's pretty good proof that you've got certainly a target, a physical target there. And if it's not behaving like an airliner and not behaving like a private aircraft, it's very well worth investigating at that point.
yeah. Yeah. Well, I also wanted to ask if you have explored LiDAR at all. That's something that someone had mentioned to me online. Now, if I understand that correctly, basically it involves pointing some kind of a laser, either visible or invisible, at a target. And that could be dangerous if it's an aircraft, right? You don't want to blind pilots. So there's that consideration. And then I think the other consideration might be whether or not you can even get a reflection from it. But I understand that LiDAR is supposed to be kind of a newer, more precise method.
Well, LiDAR operates in the near infrared. That's above the human visual
Okay.
range. For that very reason, you don't want the eye being burned by the LiDAR beam. But LiDAR beams, unless it is a scanning LiDAR, what's the probability of that little beam, like you might have with a laser pointer in the blue region pointing up in the sky? What's the probability of that intercepting a UAP type target? Probably very low. Now, they do make scanners, and these scanners do have the capability of scanning a hemisphere or something like that. And certainly it might be useful to try that. But also, unless you have a very professional LiDAR high-powered system like the military might use, your range is somewhat limited on a scanning LiDAR that you might set up on a tripod. Maybe
Okay.
maybe 5,000 feet detection range is maximum for something like that.
Yeah, so that would be kind of a more specialized application then.
Right.
Well, and I appreciate you mentioning there are so many different detection things that have come to mind. Another one that I've wondered about are the sonar systems they use on vehicles, right? Like the backup alarms and stuff like that. Tesla and others have actually been able to visualize those returns in terms of a map, but I'm guessing you probably got like 100 meters at the most in terms of range. So,
Right. In the air, the attenuation of an ultrasonic signal, and most of these backup type sensors operate at the ultrasonic frequencies, maybe, I don't know, 40 kilohertz, something like that. The attenuation is very high. The atmosphere treats that signal very badly, and by the time it gets to the target and get back to you, there's not much power there.
yeah, yeah. So again, super short range, super
Right.
limited. Yeah. And again, like LiDAR, my thought there was that might be interesting. Again, that with that police gun scanner idea in mind, I was like,
Well,
if you have a UAP, it would be interesting to be able to point something at it. But
yeah, Tim, basically, you might use a radar at 76 gigahertz, like the automobiles use for the automatic throttle control when you're in cruise control, your automatic cruise control. Those have pretty good ranges. Uh, but again, to use something like that or the Homodyne radar, you've got to be in a hot spot. You've got to have seen this thing. You've got to be operating a stakeout, just waiting for it. And then once you see it, that's when you collect the data on it.
yeah. Well, and that seems like it brings us full circle back to passive radar. So, well, Gene, I want to thank you so much for your time today. This has been kind of a great overview of some of the primary detection methodologies. I love it that you walked us through some of the the benefits as well as the challenges of using radar to detect UAP. And I want to close by asking what's coming up for you, and if people want to get involved with this, if people are interested in working as citizen scientists to try and build and operate radar, um, could they get in touch with you? Do you have any information online or anything like that?
I don't have any information online, unfortunately, but I would suggest that if a person is interested in UAPs, uh, join the SCU.
Oh,
Hopefully, in the near future, we might have a radar program associated with that organization. Uh, or there are other organizations that we might try to go with. But to get some radars in the hands of the citizen scientist, because I'm sitting here in Atlanta, there might be much better areas around the country, and we need to get these passive radars out. And so I would urge join an organization like SCU and determine if indeed uh, when we try to put radars out that determine that you might want to participate and try to get one of those radars. Yeah, you may have to buy the parts yourself. You may have to buy the uh, software-defined receiver. You may have to buy the Yagi antenna, and you have to have a computer to run the software on. But I think that's where it's all headed.
yeah. No, that is a wonderful suggestion. So let me give that URL to people. Again, it's explorescu.org. I mentioned that at the top of the show. Scientific Coalition for UAP Studies. And that it's wonderful. That brings the whole show full circle because this really started with your presentation at the 2025 SCU conference in Huntsville. So, Gene, let me thank you again so much for your time today, sir.
Tim, thank you very much for having me on your show, and let's see where all this goes in the future.